Electrophilic aromatic substitution. Electrophilic aromatic substitution. So this is a very old-fashioned reaction that's still in use. Very powerful way to make bonds to benzene and benzene-like compounds. So we're going to call it electrophilic substitution because the ring is a nucleophile and we are bringing some electrophile to it. Okay, so my aromatic ring is my nucleophile, and it's a pretty bad one. It's a pretty weak nucleophile, again, because it's so dang stable, right? It wants those pi electrons, doesn't want to give them up. And so if we're going to do this, we need a strong electrophile. And oftentimes, even that's not enough. We'll bring a strong electrophile in with an acid catalyst. And thus far, whenever we've talked about acid catalysts, we've talked about Bronsted acids, so hydrogen bond or hydrogen donors, HCl, H2SO4, sulfuric acid, that kind of stuff. Okay? And we will see that sometimes in this chemistry. But we'll often begin to see some Lewis acid catalysis as well. So electron acceptors, often aluminum compounds, titanium, iron, really electron poor compounds that want to hold onto electrons. Okay. So the first example we're going to talk about, we've actually already seen. That's nitration of an aromatic compound. Nitration. Here's my aromatic compound. As you saw me do with my own little mitts, I took nitric acid and sulfuric acid. So sulfuric acid was actually my solvent. And I added nitric acid very slowly. And what I ended up with is a nitroaromatic compound. How does this work? Here is nitric acid. If I give it some very strong sulfuric acid, where is it going to protonate? Well, most of the time here, but once in a while, it will protonate here instead. And when it does so, I have now made a leaving group, and so that's going to leave. When it does, I have a very, very powerful electrophile called a nitronium ion. This nitronium ion is now attacked by my nucleophile. That nucleophilic attack gives me this cationic intermediate. So notice there's a hydrogen on this bottom carbon that's here. I just didn't draw it. Right? This is not aromatic anymore. But this positive charge is pretty delocalized through these 5 carbons. So this is a relatively stable carbocation. Right? Eventually, something is going to come in and take that hydrogen. I don't care what it is. It could be water. It could be the solvent. It could be anything. It's going to take this very acidic proton, and that gives me my product. So again, my strong acid makes my electrophile a much better electrophile, and then that electrophile is attacked by my weak nucleophile, and I get my product. Now you might be wondering, why do I see para and ortho products here, but I don't see meta? Well, again, if you remember back the stuff that we covered in the first lab, it might ring a bell. If we look at the cationic intermediates for these reactions, here, both the para and the ortho-going intermediates have cations that are stabilized by the oxygen lone pair. All right, so oxygen is stabilizing both of those cations, making them easier to get to and easier to get through. However, if I look at this meta case, right, this is the intermediate that would give me something meta. I can't draw this intermediate to put the charge at that carbon next to oxygen. Right? There's no way for me to take this lone pair and push it into the ring in such a way as to stabilize that cation. Right? So we call compounds like this with lone pairs and donating groups, like this oxygen, that have a lone pair they can push into the ring, are ortho-para activating. So the reaction goes faster than benzene, and B, the reaction goes regio-specifically to both the ortho and para positions. And sometimes sterics will push it more to para than to ortho, but usually you might see a mixture of ortho and para. Okay? These are examples of donating groups, so nitrogen is a little bit more donating than oxygen. If you put a carbonyl next to the lone pair, it's less donating, right? Because I'm pulling the lone pair away from the ring and toward something else. And finally, plain old carbon, like a methyl group, is a pretty decent activator as well. So if we try to do this with just a CH3 here, we'll also see primarily ortho and para position for the nuclear, for the electrophile. Alkyl groups will tend to also give us ortho and para substituted products. You might remember that our first lab was taking benzonitrile and treating it to these conditions, and we ended up with meta-nitrobenzonitrile exclusively, only, no ortho, no para. Why is that? Well, we have the same kind of intermediates to look at, but now instead of an oxygen stabilizing this positive charge, I've got a really electropositive carbon here repelling this positive charge. So having these two positive-ish things next to each other is destabilizing. It's bad. Over here, I don't have that problem. Again, there's no way to put that positive charge is primarily here, and here, and here. It's not really here. Okay? So electron withdrawing groups have the opposite effect of electron donating groups, which, yeah, okay, that tracks. And so we can say that electron withdrawing groups are ortho-para deactivating. And so in that way, they're meta-directing. And this is an important distinction, all right? So yes, the cyanide means that I'm only going to see reaction at the meta position. It's not that the nitro is making the meta reaction faster. It's that it's making everything else terrible, right? So that's like if I have 3 roads leaving my house, and I want to sort of emphasize taking one road, right? I can either improve that road, or I can burn down the other roads, right? Giant roadblocks and fire and everything else, okay? So these withdrawing groups are not making the meta reaction faster. Actually, they're making it a little bit slower, probably. But they are really killing the ortho and para rates, right? So overall, the reaction is slower. It's ortho-para deactivating, and so in that way, it's meta-directing. So if I have a donating group, I'll see ortho-para substitution, and it'll be fast. If I have a withdrawing group, I'll see meta-substitution, and it'll be slow. One quick thing I wanted to throw in here. Somewhere between donating groups and withdrawing groups are the halogens, in particular chlorine and bromine. So those are kind of weird exceptions. They are deactivating. They make the reaction go slower, but they are ortho-para directing. So you end up with ortho-para substitution, but it's not activating. It's actually slightly withdrawing. That's a weird middle ground because these things kind of withdraw electrons in a sigma sense. These are polarized bonds, but they've also got lone pairs that they can push into the ring. And so that weird kind of push-pull thing makes them a strange middle case. So one really important example of this reaction. This is methylbenzene, better known as toluene, important commodity chemical. When I take nitric acid and sulfuric acid and treat that with toluene, I very quickly, I have an activating group here, going to get nitration, mostly at the para position, but some at the ortho position as well. Now, if I keep heating it, I'm going to put a second nitro compound on here. Now, obviously, this nitro is a withdrawing group. So this is going to make this reaction slower, which is why I need to keep heating it and maybe increase the heat. But I can force a second nitro compound, or a second nitro group onto that. And of course, it's going to be in that ortho position. If I keep heating it, nitros at the ortho and para positions. So now this is trinitrotoluene, or TNT. Dynamite. One more reaction I want to talk about. It's very similar to nitration. This is sulfonation. So again, the most common use of this starts with toluene. I'm going to give it concentrated sulfuric acid, and I'm going to heat it up. Now, this is sulfuric acid. So it's nobody's base, but a lot of times, or sometimes, it can get protonated by another molecule of itself. When that happens, now I have a leaving group. When water leaves, and sulfuric acid will certainly soak up any water that's formed, I'm going to get this really cationic and unstable intermediate, very similar to the nitronium ion intermediate. And this reaction will work exactly the same way. We'll attack that. Just like NO2 added to the ring earlier, now I'm adding SO3H to the ring. And after it loses that proton, it gets back to an aromatic compound. I have a sulfonic acid. And this one in particular is toluene sulfonic acid, or tosic acid, sometimes abbreviated HOTS. This is a really, really strong acid. The pKa is about 0. So that puts it on par with your HCl in terms of acidity. But this is a nice organic crystalline compound. I can weigh it out. I can keep it dry. There's no water involved if I don't want there to be. And so this is a nice, convenient organic acid that's used very often as an acid catalyst in a lot of reactions, particularly like esterifications and such. So sulfonic acids, very acidic, gives me a lot of water solubility there, obviously. And the mechanism for putting on very similar to nitration.